So, this module we are looking into details of unsteady flow in one dimension, and we are taking the shock tube problem, and we had discussed in the previous class the various flow features that are encountered in a shock tube. It starts with the initial condition that there are two sides to a shock tube. It is essentially a tube. You have the high pressure side, which is called the driver side, and you have the low pressure side, the driven side, and at t equal to 0 the interface between these two sides is suddenly ruptured or taken away. You have very high pressure being interfaced to very low pressure gas, or high pressure and low pressure. This high pressure differential essentially creates a shock, and the shock moves into the driven section. You have other waves and flow features also in the shock tube. An expansion fans move towards the driver section, and the region in between, which is a interface between the driver gas and the driven gas, shock process driven gas, is the contact surface, or contact discontinuity. The shock, as it goes through the driven section, compresses the gas as well as carries gas along with it. It produces mass motion. So, our idea here is to look at this complete problem and solve various regions and then put them together to look at a shock tube as a whole. Okay. So, the first part of this is the moving shock that is already covered. So, now let us start moving into the left hand side of the shock tube that we have been looking at, which is the waves. So, the expansion waves. So, expansion waves, before we go there, we start with simple waves, waves of very small amplitude, waves of infinitesimal amplitude, very small amplitude, and look at the analysis of those waves. Okay. They are representative of sound waves, and you can soon we will show their equations are contained within the system of flow equations that we are discussing. So, there is general equations of motion for an inviscid adiabatic flow. So, this is an inviscid flow. So, viscous effects are not considered. It is a compressible flow. So, we have the compressible equation. So, dou rho by dou t plus del dot rho v is equal to 0. This is continuity, and rho dv by dt is equal to minus gradient of pressure del p. This is momentum, and these movement of these waves are isentropic. So, S is, so entropy does not change, ds by dt equal to 0. So, consider a quiescent medium where there is initially there is no velocity and some small disturbance, small changes in density or velocity or pressure is introduced. Okay. So, delta rho and delta u, small very small changes in density and velocity are introduced. So, they are small perturbations, and so the undisturbed or the quiescent flow medium has rho infinity and u infinity, p infinity and t infinity as properties, and if you take a quiescent medium, u infinity is, this is equal to 0. Okay. So, now what we are trying to do is to see how this these small changes propagate in the medium, and we consider only the one dimension. So, we are only considering one dimensional case here. So, let us write the equations for these small perturbations. So, rho, the change in rho is rho actually is rho infinity plus the small perturbation. u is u infinity plus delta u, which is, since u infinity is 0, is basically delta u. Now, the guiding principles here is that we consider changes to be, or the terms in the equations to be significant if you have significant terms, multiplications like dou delta u by dou x, these terms are significant. But if you have multiplications of small quantities, delta u multiplied by delta rho, these are both are small quantities, two small quantities multiplying each other, they become very very small, so they are taken to be 0. Okay, so this is the guiding principle, and once you apply these principles to the equations, then we can see how they get transformed to the evolution equation for delta rho or delta u, that is the small perturbations. So, we take the continuity equation dou rho by dou t plus dou rho u by dou x. This can be written as using principles of differentiation, rho dou u by dou x plus u dou rho by dou x. Okay. So, now rho is rho plus delta rho, and u is dou delta u. Okay. So, we get these terms. Now, this is directly by substituting these values into the equation, and now we can use these principles. So, you see that there is a dou delta rho here, this term is significant. Rho infinity is the quiescent medium's density, this does not, I mean this is a constant. So, dou rho infinity by dou t is 0. Okay. So, you can use those principles here. So, now if you look at this, a multiplication of delta rho with delta u, dou delta u by dou x is going to be extremely small. So, that is not significant, and rho infinity multiplied by dou delta u by delta x, dou u by delta u by dou x partial derivative is significant. So, using these guiding principles, we can write down this equation in terms of dou delta rho by dou delta t, rho infinity dou delta u by dou delta x, and this term is extremely small, and you have the other term delta u by this term is also extremely small. Now, so this yields basically dou delta rho by dou t plus rho infinity dou delta u by dou x equal to 0. This is what this equation yields. Now, if you take the one dimensional momentum equation, rho dou u by dou t plus rho u partial u by partial x equal to minus dou p by dou x. Now, this being an isentropic flow, so pressure can be related to density by the term. So, p is a function of rho in general, you can write p is a function of rho and s. If so, dp is dou p by dou rho at constant entropy d rho plus dou p by dou rho at constant density ds. Okay. So, here ds is 0, so it is isentropic flow, and this term dou p by dou rho at constant entropy, this is nothing but speed of sound a square. So, this term can be brought inside the equations, and thereby dou p by dou x can be converted to a square d rho by dou x, that is partial rho by partial x. So, that is what is done here. So, it has been converted to the changes in density, and now a square in general can be a variable. So, but for the quiescent medium there is a speed of sound which is a infinity corresponding to the temperature T infinity. You know, a infinity is square root of gamma r T infinity. Now, if there are small changes to pressure, temperature, density, correspondingly we would expect small changes to A infinity, and therefore we need to consider them into the equations also. Okay. So, now you can write considering so now rho is again rho infinity plus delta rho, u is delta u, and you can substitute them, again follow the same guiding principles that such delta rho, delta u, these terms are very small. Again these terms are very small, this term is significant, this term is small. Okay. So, and this term is significant. So, there are two significant terms over there. Now, this is very weak waves, infinitesimal amplitude, very small perturbations. Now, A, that is A is again, that is speed of sound, is a thermodynamic quantity. It can also be written as a function of density and entropy. Now, entropy is constant, so it becomes a function of density, and it can be expanded by a Taylor series kind of an expansion. A square is A infinity square plus dou A square by dou rho, rho minus rho infinity. So, this is basically delta rho, and higher order terms which are very small. Now, this term here can be substituted for A square in the momentum equation. But again we find once you carry on the multiplication, you have small quantity delta rho multiplied by another small quantity dou delta rho by dou x. So, they are again very small. So, finally the most significant terms of the momentum equation is minus A infinity square dou delta rho by dou x. So, you have two equations. The first one comes from continuity and the second one comes from momentum, and these equations are now the equations for evolution of an extremely small perturbation in a quiescent medium, and that is typical of a sound wave. And can we get the equations of sound wave from here? You can do that. You can just so if you take a partial derivative with respect to time here for this equation and take partial derivative with respect to x here. So, you get dou square del rho by dou square t is equal to minus rho infinity dou square delta u by dou x dou t, and minus A square dou square delta rho by dou x square t square is equal to rho infinity dou square delta u by dou x dou t, and comparing these two equations you get dou square delta rho by dou t square is equal to A infinity square delta rho by dou x square, which is what is written here as nothing but a wave equation. Wave equation where the speed of the wave is A infinity square, which is the speed of sound waves in that particular medium. So, the solutions to these equations in general are of the form f x minus A infinity t plus g capital G x plus A infinity t, that is delta rho, the small change in density. You can get the same equation, the same wave equation for the change in velocity delta u, and these are given taken to be small f and small c functions. This is a D'Alembert solution to the wave equation. So, where x minus a infinity t and x plus a infinity t, they represent the directions of propagation of an initial disturbance. So, that is given over here, you can see. So, this is the initial propagation. Okay, so they move in this direction. So, you can write down these solutions. This is normal, I mean this is the wave equation that is linear and solved in classes. So, now let us see how the various quantities, that is density and velocity, they are related to each other, as well as changes in pressure. So, when you look at them, so if you say delta u, consider for a general case, let g be equal to 0, that is the small function with small letter g equal to 0, then delta u is f of x minus a infinity t. Dou delta u by dou x is f prime, is a differential of f, while dou delta u by partial t is minus a infinity f prime. So, from comparing these two, we get dou delta u by dou x equal to minus 1 by a infinity dou delta u by dou t. Okay. So, now this can be combined along with the continuity equation. So, continuity equation is dou delta u delta rho by dou t plus rho infinity dou delta u by dou x. So, from the previous equation you can write this as dou delta rho by dou t minus rho infinity by a infinity dou delta u by delta t. This can be taken together. Delta rho is rho infinity and a infinity are constants for this problem. This is equal to 0. Okay. So, this implies that this term here is a constant, delta rho minus rho infinity by a infinity delta u is equal to constant. Now, this constant can be evaluated by taking the equation for the undisturbed gas, and there when you started off with delta rho and delta u both were zeros. Hence, at initial this is 0, therefore, it is constant. So, this constant is 0, and so it relates delta u to delta rho, that is change in density a infinity by rho infinity. So, this is the equation. So, you can evaluate how much change in velocity is produced by a small change in density. Now, because this is motion of sound, delta p by delta rho is a infinity square, small pressure perturbations, you can use that and relate change in velocity to change in pressure. So, in general, so we started off with the general equation delta u is f of x minus a infinity t plus g of x plus a infinity t, and we set g equal to 0. We can also set f equal to 0 and get other forms of this equation. So, in general you will get delta u is plus or minus a infinity by rho infinity delta rho, and delta u is equal to plus or minus delta p by rho infinity a infinity. So, these are very small changes what we are talking about in this. So, this is infinitesimally small, and these are corresponding to sound waves, which is very small, and when pressure increases, density increases in the sound wave, that is compression. So, that is the compression part of the sound wave, and when the pressure decreases, then that is called the rarefaction part of the sound wave. So, this some of these things known to you, but now we have seen that these waves are also part of the fluid dynamic equations that we have for the general fluid flows, and we saw how waves fit in there, and these waves are extremely small in amplitude. Now we move on. In the next class we will move to finite amplitude waves, where waves now have significant strength in their pressure changes or density changes or velocity changes. Now in this, what you noticed was that you get finally the wave equations. So delta rho by delta t square is equal to A infinity square dou square delta rho by dou x square. This is a wave equation with A infinity speed of sound, that is a constant. So this is the case of infinitesimal waves. When we go to finite waves, we see that the speed of sound at that is not a constant anymore. It can change from point to point, time to time. So that is going to be the additional complexity that comes into picture. In this, if there was an initial wave form, it just propagates along these lines. These are lines of propagation. They are also known as characteristics, and this methodology, that is the way they propagate along certain lines, known as characteristics, will be very useful when we look at finite amplitude waves. Here x minus A infinity t and x plus A infinity t represent two sets of characteristics, okay, along which the solution propagates. Since A infinity is constant here, these characteristics are straight lines, but when we go to finite waves, we will see that that need not always be true. So in the next class we will go to finite amplitude waves.